I'm delighted to present our work, titled A Multitask Framework for 2D Scene Parsing and 3D Reconstruction in Indoor Space Documentation. Smart indoor environments for human comfort and well-being increasingly rely on detailed spatial information and representations, but laser scanning of an environment can be costly and the point clouds sometimes miss semantic annotations and details. On the other hand, there is missing research to produce 3D spatial information and representations from limited data without sensors and research inputs. Our research addresses this gap by proposing a multitask learning framework that generates 3D point clouds and fine annotations from a single image by combining 2D scene parsing and 3D reconstruction techniques that enhance depth estimation, surface modeling, and 3D learning for environments where sensor data or manual annotations are missing. To the best of our knowledge, this work uniquely combines 2D and 3D segmentation networks with the support of LLMs. The proposed framework offers robust solutions for 3D surface reconstruction, learning, and broad applicability in real-world cases, simulations, and digital twinning. So, the main framework proposes a pipeline for single-shot surface reconstruction and generating 3D segmentation masks from 2D scene parsing dataset that is generated via single images from TUM Campus, by producing depth and segmentation masks to facilitate domain adaptation between 2D and 3D. The produced pairs are used for 3D reconstruction by the generation of 3D meshes and masks. These meshes as well as existing point clouds are introduced to 3D segmentation networks in the generation of annotations. The techniques ranging from 2D scene parsing to 3D reconstruction enabled the generation of 4D media and real-life applications for simulations, and even action recognition for future work. Let's go into detail about the grounding research that motivates this framework. There's a growing need for accurate and efficient 3D data to support spatial analysis and smart decision-making. Traditional modeling provides high precision but remains labor-intensive and difficult to scale for large or real-time projects. The challenge of creating reliable digital models often lies in interpreting point cloud data about features like walls and columns that can be time-consuming. Recent advances in deep learning approaches have greatly improved 2D scene parsing, object recognition, and make it possible to automate the 3D segmentation. Innovations like neural radiance fields have pushed 3D modeling forward by enabling photorealistic scene reconstruction from just a few images. Other methods use voxel-based modeling to track movements and actions in space, supporting automated monitoring and safety applications. By integrating these technologies with advanced sensors and smart learning models, we can now create digital twins, real-time simulations, and adaptive indoor systems transforming the world we document and manage. The framework employs various neural networks for specific tasks. For instance, Depth Estimation Network uses VITL encoder and DNOV2 decoder. And Semantic Segmentation Network implements a VITL encoder and Mask2-Former decoder. Then, the multitasking learning framework has been developed for 3D surface reconstruction. Attention-based filtering and feature extraction methods are used together with LLM to code by user prompts, based on the paired information in generating 3D meshes and masks. A dedicated 3D segmentation network built upon the PTV3 backbone, and a VIT-based decoder is introduced, with Vision Language Model to incorporate diverse 3D datasets, such as S3DIS and ScanNet. So, 3D networks are also part of evaluation and performance assessment of accuracy, ensuring optimal performance of the 3D reconstruction. So, 2D scene parsing dataset is generated as a benchmark in 2D understanding of indoor point clouds. 2D segmentation annotations are derived from 150 class-colored RGB format of AID20K dataset by VITL plus Mask2-Former architecture and SERNet-Former methods. The depth information of each raw image is provided as grayscale.png files, including pixel values between 0 to 255 with the same sizes of images. Depth information is similarly completed via VITL plus DNOV2 architecture. The methods applied in the optimization of 3D reconstruction can be briefly presented as scalar fitting and thresholding on point clouds, corner detection such as Harris algorithms, and most effectively, the optimization of mask mesh pairs with the help of large language models. One effective approach in optimizing 3D reconstruction involves planar fitting and scalar adjustments. Filtering methods, such as scalar thresholding, are applied to these estimations for error correction. Additionally, pairs of depth and segmentation masks allow us to refine depth values at specific object surfaces. Corner detection algorithms, like the Harris corner detector, further define spatial constraints and improve parameter selection. Initial results show that applying spatial constraints almost perfectly align with real-world scenarios. Finally, attention-based methods and LLMs use segmentation masks from 2D scene parsing to set mask mesh boundaries and user-defined spatial constraints, boosting the precision of depth predictions. So let's dive deep into the detail of 3D reconstruction via large language models. Based on user prompts, large language models optimize depth information at certain coordinates. The information from segmentation masks are reapplied for generating 3D surface meshes and masks. The pairs of optimized depth and 2D images are introduced to create exact 3D surface meshes. Similarly, segmentation masks are applied with depth inputs and 2D segmentation masks to derive exact 3D surface masks. Some of the boundaries and values from the earlier thresholding help to define and generate user prompts, such as the prompt, below 160. And the predefined boundaries with the help of segmentation masks help to introduce the features of surfaces by user prompts to LLM. By using LLM, depth information is optimized and used in the 3D reconstruction pipeline. The generated surface mesh is validated with 81.55% accuracy with regard to the existing point clouds. And Ream's score returns 0.02. The resultant 3D surface meshes and masks are introduced to the segmentation network with the help of VLM for different classifications, datasets. So, it becomes possible to segment any mesh, formatted with regard to S3DIS, SERNet, or any datasets for domain adaptation like AID20K to point clouds. So, let's have a look at what is acquired in the experiments on the pre-trained neural networks on 2D and 3D datasets. Our models used in 2D scene parsing set state-of-the-art results on datasets like AID20K and SUN-RGBD. And on 3D, the trained networks are also tested on S3DIS and SERNet, with the results in Table 3. The constructed network is trained for 100 epochs with a mini-batch size of 6, utilizing the Atom W optimizer with a momentum of 0.9, using NVIDIA 100 GPU. In 3D reconstruction, our method achieved state-of-the-art results, delivering the lowest RMSE on the TUM-CMS indoor point clouds dataset. This is further supported by planar and pixel-wise accuracy, reaching up to 82%. These strong results motivate to advance for domain adaptation from 2D to 3D. In brief, 2D segmentation masks help recognizing objects' exact shapes, borders in 2D and 3D as well as the complexity of surfaces like walls, doors, and voids. The multitask framework enabled the implementation of single-shot 3D reconstruction in a BIM-based simulation and comfort control as a use case by our method with promising results in recognizing tiny objects with their annotations to improve the task-oriented simulations for well-being and user occupancy. The recent real-life practices by our framework enabled to annotate and segment different classes such as stairs, balustrades, and it becomes possible to export BIM software for spatial analyses and design, as the basis for domain adaptation between multidimensional and multi-scale datasets for simulation, 4D analyses, action, and feature-based recognition. Optimizing focal depth increases depth estimation's precision based on the applied filtering techniques. Here we see that it is also possible to work at outdoor scale and recognize, segment outdoor objects such as buildings, trees, streets, as well as smaller signs, cars, and people, that grounds for spatial recognition in smart cities and support autonomous systems and environments. The developed framework reconstructs almost any scene precisely iterated through a few supporting steps. The precision and resolution of the results are very open to growth and gets better and better. That would be fitting top real-life application as real-time models. So, it becomes possible to adapt our framework for BIM and domain adaptation research, besides 3D and 4D analyses from 2D single images. To conclude, this research presents a new multitask learning framework, bridging 2D image and 3D point clouds. Based on the framework, 2D scene parsing dataset of TUM-CMS is generated. 3D reconstruction techniques are developed, enabling segmentation masks for 3D. 82% MIOU precision and 0.02 RMSE results are acquired on TUM-CMS dataset. Transfer to BIM and domain adaptation by data exchange between different datasets, media, inputs, and dimensions become possible. 150 class 3D point clouds is generated by 3D reconstruction. The framework enables learning 3D reconstruction data through segmentation networks and is adaptable to multimodal learning, to be used in many use cases that we currently work on.